Alright, let's bust out this review packet. Hopefully won't need to do multiple takes. So, question 1 on the review packet. We got vector u is 1, -3, v, -4, -5. We're being asked to find the projection. So I'm just going to use the formula right there. So projection equals dot product over magnitude of v squared times vector v. Alright, so dot product is 1 times -4 plus -3 times -5 all over the magnitude of v squared. So the magnitude of v is the square root of a squared plus b squared. So down here I really just need to do a squared plus b squared. I forgot what I was doing for a second. I don't know. I'm a mess. And then I just multiply that by vector v. Okay, so I just need to do a little bit of math, figure out what these numbers actually are over here. So -4 plus 15, so this is 11 over 41, I believe. And then -4, -5, and then I just distribute that through. Ta-da! Done. Yay! That was so much fun. Hope you enjoyed my waiting music. Alright, question 2. There's actually 2 different ways of doing this one. There's the way that I did in the answer key, and then I'll show you a second way. Alright, so we got 2 different people. They're pulling a puppy. And I should have actually drawn this the way it is in the picture that I gave you, because the puppy is directly horizontal, and that makes a big difference in how we're calculating it. So if this is 18, this is 15, this is 23, and this is 27. So basically, I have 2 different people, one up here, one down here, and then here's the cute little puppy. And if I just find this person's vector, which is 23 cosine 18, 23 sine 18, and I know that because that's one of the ways that we do component form. This one would be 27 cosine, and I could use either -15 or 345. I'll use -15 this time around. And this only works because the puppy is exactly horizontal right now. So if I just add these together, that's going to give me what the puppy actually equals. So I'm doing 23 cosine 18 plus 27 cosine -15. That's going to give me like 47.99. 23 sine 18 plus 27 sine -15, and that gives me 0.12. And then I just need to find the magnitude of that puppy, not the projection. Puppy. Okay, so a squared plus b squared, giant square root of that, and you just get 47.95 pounds. So that is the first way of doing it. The second way of approaching these ones is when it's not directly horizontal like this. You have to do something slightly different, okay? So you end up getting the same answer in this case, but we'll see. So here I have 2 different things, and then I have the puppy in the middle here, okay? And what we have to remember is that the way that vector addition works, and I'm going to use a different color if I can write this down and talk at the same time, which I can't. So vector addition says that I can take this side and I could put it right here, and I can take this side and put it right here, and this makes a giant parallelogram, okay? And the reason that this is useful for us is that we know that if we add these together, so we're going to get 33 or something like that, maybe? I don't know. I'm doing this without a calculator right now. We get 33. We could figure out what this side is over here, so that's going to be like 147, maybe? I don't know. That's 23, that's 23. And we now have a big old triangle right here. And we can use law of cosines to find that side length, which is going to be the magnitude of that side. So if we did this, 27 squared plus 23 squared minus 2 times 23 times 27 cosine 147, giant square root over all of that, we'd get that same value of 47.95. So that's how you would approach this situation if it wasn't presented to you like they were horizontal in this case. Let's scroll up. Ooh, airplanes. Yay, so much fun. Love them. 3. Blah, blah, blah. Airplane heading north 30 west. Okay, so that's this way. And I don't like to add in any sort of bearings. So I wouldn't necessarily write that that was 30. I would write that this is 120 because the direction angle comes from positive x-axis around. And that's my plane. Let's see here. We got wind coming up next. Wind is going north 45 east, so that's going to be right here. Again, north 45 east would be up here, but I'm going to write as a direction angle. And then I want to know where the resulting plane is going to end up, basically. So the plane thinks it's going that way, the wind is pushing it this way, so it's probably going to be like somewhere over here, maybe in quadrant 2. Not positive, to be honest with you. So let's just write these vectors. So the plane is going to be its magnitude, which is 500. Cosine the direction angle, 120. 500 sine 120. And we'll do the wind. It's going to be 70 cosine its direction angle, 45. 70 sine 45. And if I add those together, it's going to give me the result. Okay? So I'm literally just typing these in my calculator as is. I'll get negative 200.5. I'm going to store that as the letter A in the calculator. I get 482.5. Okay, that was a little bigger than I was expecting it to be. I'll store that as B. To find how fast the plane is actually going, so it's ground speed, because remember that that's what this one is the ground speed, versus this one is the air speed. I just do the magnitude. And since I've stored these as A and B, I can literally just type this formula in the calculator, square root of A squared plus B squared. That's going to give me 522.5 miles per hour. Okay, so that's one of our lovely answers. Now, next is we need to find the course, which basically means the bearing. So from looking at this right here, this is in quadrant 2. A negative x value, positive y value. So when I go to figure out what this reference angle is, by just drawing this triangle and using y over x, and find theta, so theta as a reference angle is going to be 67.43. Well, I know that that's right here, okay? So as a bearing, I need to swing all the way around. So it's two ways of looking at this. I need to either come all the way around, and that would be a traditional bearing, or what I'm going to do in this case is match their format. So they're using the fancy format where we would say from north heading towards the west. Okay, so north something west, and it's always north and south, and then east or west over here. It never starts with an east or west. Always starts with north and south. So if that's the reference angle, I need to figure out that guy. So I'm just going to do, in this case, 90 minus that theta reference, which is going to give me 22.6 degrees. So this is the fancy bearing. This is the ground speed. And if I wanted to do the non-fancy bearing, I would have just done 270 plus that theta value. And that would be how I get a bearing in the second quadrant. Hope that made some sort of sense to you. Oh my god, there's so many of these. Need some background music, but then I'd get copy struck on YouTube, so... Let's see, today's playlist is High School Musical, okay? I'll let you play that in the background. 4 is a slightly harder type. So we still have a plane, we still have wind, and then we still have the ground speed, or this result that happens here. So the reason that this one is slightly more challenging is because we know which way we want to be flying. So we want to be flying due west, okay? And we don't know how fast we're going, but we do know that direction. And then over here for the plane, we know that we're flying 400, but we don't quite know which way it's pointing. That's what we're going to try to figure out, is which way we need to point ourselves to make sure that we actually fly west. And we have a 35 mile per hour wind, bearing of 240. Okay, so bearing, that'd be 90, 180. This would be 270, so I know it's going to be somewhere right here. And it had 30 to go to get there, so this is going to be at 210 degrees. All right, so I'm going to write that one first because I can. Wind is 35, cosine 210, not 120, 210. 35 sine 210. The plane. So let's think about this. If the wind is pushing down, then I need the plane to point up a little bit, so that if the plane's pointing up, the wind will push it down and I'll end up going west. So I know that the plane's probably going to be somewhere up there, but I don't actually necessarily need to know exactly where it is right this second, and I can just write 400 cosine theta, because I don't know that angle yet, 400 sine theta. And if I add those together, I'm going to get the result. Now, we know something about the result. It has to be going directly west, which is in the x direction, and it can't go vertical at all, so 0 in the y direction. And now we have our setup for a basic equation. We know that the x values add together to equal each other, and we know that the y values add together to equal each other. If I look at this one, there's only one unknown. Here there's theta and x, so I'm going to deal with this one. Okay, so I will just have 400 sine theta plus 35 sine 210 has to equal 0. I will subtract 35 sine 210, divide by 400, do sine inverse, and when I do that, I'm going to get a reference angle of, I think it was negative 2.5, and we can just make that positive because we don't care about negatives when it comes to reference angles. And we've now need to figure out exactly where this is. So we've already reasoned that it needs to be up here, right? That it needs to be in the second quadrant. So for bearing, that comes all the way around. So that means I'm going to do the reference angle plus 270. Okay, because I'm starting from north, 90, 180, 270 plus theta, and that will bring me to where I need to be. And that will be our actual direction that this person needs to fly in order to end up going west. So 272.5 degrees. And I don't remember if this question asked you to find the x value, but I will just for practice. I can't remember if it asks you, but what I would have to do here is very carefully figure out what this theta value actually is. So theta's really here. So I would do, that was a fun noise. I would do 180 minus that theta reference, and that's what I'd be putting in right here, because this is direction angle, not a reference angle or a bearing angle. So, and then I would just add that to the 35 cosine 210, and whatever that equals for x, it's going to be a negative number. I believe it's going to be negative 369.3, and that's because we're going west, so it's negative, so the magnitude of that value is just going to be positive. So this is how fast the plane is actually going. So the wind is slowing it down pretty significantly, 30 miles per hour. Woo! Finish that one up. There's just so many of these. Oh, God. I'm tired. All right. The this is number 5. We have some sort of plane, we have some sort of wind, we have some sort of result. Let's see, planes traveling airspeed, heading of 75. Okay, so that's going to be right here. That means that we're going to have 15 degrees as its direction angle. So I can write plane is 270 cosine 15, 270 sine 15. Let's see, wind is coming up next. Wind is blowing 27. Compass heading 165, so that's going to be right here-ish, and that is 75 past that when I'm doing it. So I'm going to use negative 75. Okay, so that's going to be 72, lots of 7s in this problem. Negative 75, 72 sine negative 75. Add those together to get the result. Okay, and let's see here. We're going to get 279.4 and 0.33. So magnitude of that, a squared plus b squared square root. I'm going to get 279.4 because that's very small. So this is essentially saying that the plane is flying pretty much due east, which means that its bearing, which we weren't asked for, but just an FYI, its bearing would probably just be 90 degrees because we're pretty much just flying east, maybe slightly less. Whew, yay. Do 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 do. I stop writing so close to my little cheat sheet over here. Oh, can't use. We got water going on here. All right, boat with ground speed 16, still water, crossing a river perpendicular. Okay, so I always like to draw rivers vertically so that downstream is a little easier to visualize because it's literally down on my piece of paper. And let's see, we have a boat with a ground speed of 16 miles per hour is crossing a river perpendicular to the current. So we have a boat going this way. It is capable of 16 miles per hour. There is a current going downstream. So I'm going to write that right there. And it is 6 miles per hour. What angle is the boat pushed off course? So there's going to be lots of different answers here. So what we're really going to focus on is what the reference angle is that we get. So if a boat is going this way and the current is pushing it that way, it's going to end up going at an angle, right? So even though the boat thinks it's going perpendicular, it's actually getting pushed downstream. So what I'm going to find is just that angle right there, because that's how much it's being pushed off of perpendicular, okay? So straightforward, I'm just going to say tangent theta equals 6 over 16. So theta is going to equal tan inverse of 6 over 16. And I'm going to get this as a little reference angle right here, 20.5 degrees. And I'm going to say that's the answer. Now, if you drew your river going this way, okay, then you're going to have slightly different things. If you had your current going this way, you'd be going that way. If it was that way, you'd be going that way. Either way, this theta value should be the same no matter where we are. Doesn't matter which way you draw your picture, okay? More boats. Okay, so here's my river going downstream of 4 miles per hour. There's a boat with a ground speed of 22, and we want to go this way. So this is the way we want to be going. And what we'll have to do for that to happen, right, is if the current's pushing us down and we want to go sideways, we actually have to go up so that as we go up, the current pushes us so that we go straight. So this is the way that we need to actually go. So that's going to not be 16, that was the last problem. That's going to be the 22 that this boat is capable of, and this is what I want to find then. So what direction? Again, I'm just going to find this theta value. So in this case, it's sine theta equals 4 over 22. So I'll just do sine inverse of that junk, and I'll get a little reference angle here of approximately 10 degrees. So the boat needs to angle itself 10 degrees upriver so that the current will push it so that it moves straight across. Oh yeah, these guys are fun and easy. Alright. Readjust sitting on the floor doing this. Need to find a way to mount this on the wall. Alright, so every single one of these types of force and weight problems are set up the same way. I draw this little picture. I have the angle of the hill ends up being this angle right here. The force is up top. This is the work. This thing right here is officially called the normal force. And the normal force is actually what you're feeling right now, wherever you're sitting, whatever you're touching. It's what's preventing you from going through that. So the normal force that I'm feeling is on my hip as I'm lying sideways on the ground here. And it's quite painful. Box, 99 pounds, 89 pounds. Okay, so here's the weight going straight down on a ramp of 55, so this is going to be 55. What force is required to keep it from sliding down? So here's my setup. I just have sine 55 equals force over 89. Multiply 89 times sine 55 in the calculator. The force is going to be 72.9 pounds. Done. Same setup for 9. Okay. This time we got 240 pound box, 36 degrees. That's going to be 36 degrees. Trying to find the force again. So sine of 36 equals force over 240. Multiply the 240 to the other side. This force is going to be 141.1 pounds. 10, I think, is maybe different. Nope, same exact thing. Super easy. Why would I give you 3 questions that are all identical to each other? No idea. Ooh, but this is fun. This is a non-calc question. So this is a 30, 60, 90 triangle. And let's see, across from 30, this would equal the x side. This would be the 2x. This would be the x rad 3 side. So I know 2x equals 250, so x is going to be 125. So the force is going to be 125 pounds, and I didn't need my calculator to figure that out. Variation on this question, which is what I thought one of these would have done, is that I give you the force and ask you for the weight. So in that case, then we would know the top number and not the bottom number. There we go. Work. Work, 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 work. Do, 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 do. Do, 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 do. All right, 11. We're doing a work question, which is force cosine theta times the distance. They told us that the force is 10 pounds. And we're going in a direction of 7, 9. Moving the object 6 feet, so that's that. And we're moving it from 0, 0 to 6, 0. So that's in the horizontal direction. So if I'm moving in the horizontal direction, what I'm going to do is just pick any point I want on this horizontal line. So I'm going to pick the point 1, 0, and I'm just going to turn that into a vector, and that's going to capture the direction. Okay, so I used the unit vector in the horizontal direction. And the reason I did that is because now I can figure out what cosine theta is by using the angle in between, which I didn't write in any of my notes over here. I'm a mess. It's dot product. 7 times 1 plus 9 times 0 over their magnitudes. All right, so 7 squared plus 9 squared, giant square root of that is 130, and 1 squared plus 0 squared, square root of that is just 1. That's why I used that vector, so I didn't have to think about it as much, times 6. Let's see, just type all this in the calculator. You're going to get 420 over the square root of 130, which is approximately 36.84 foot-pounds. Woo! And we're done. So hardest part about this one was identifying the horizontal unit vector as one of the vectors that we could use to help us find the angle in between. Just leave that formula up there. Okay, 12, still doing force. times cosine theta times distance. This time they tell us that the force is 34, acting in a direction of 3,7, moving an object 3 feet. Okay, so that's the distance along the line y equals 2x. Okay, so what I'm going to do is turn that slope into a fraction and then write it as a vector. So the x value is 1, the y value is 2. So this vector captures a slope of 2x. So I'm going to use that vector to help me find cosine theta by doing the angle in between formula. So I get 34 times the dot product, 3 times 1, plus 7 times 2, all over the length. So that's going to be square root of 58, and this is the square root of 5, and then times that 3 there. And I'll just type all of this into the calculator. I get on top 1734 over the square root of, what does that say, 290. And then if I type that in the calculator, 101.824 foot-pounds. Done. Do 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 do. That's literally the only part I know of that song. Find the work done by force of 50, acting in the direction of negative 3, 5, moving an object 8 feet along the line y equals negative 1 half x. Okay, so I'm going to turn this into a vector, and it actually does not matter which one I let have the negative sign. I could use either one of these, and those are both going to capture the direction as far as I'm concerned, but I am going to think about that a little bit more because I do want this to work out a little bit nicer, I think. I'm not sure if it would actually matter if we used one over the other. I'm not positive. So I'm going to use this one, and that's mainly because I have a visual of what this looks like. So here's the line y equals negative 1 half x, and that vector negative 3, 5 is over here. Okay, so I'm using this point because that's going to be a point that's over here. So it's going to be a vector that's pointing in the same direction. I'm honestly not positive what happens if you use the other one and whether you get the same answer. So if you're super bored, you could do that and then leave a comment. Oh, and don't forget to like, subscribe, and push that little notification bell. Alright, dot product. I'm going to get 6 plus 5 over square root of 34 times the square root of 5 times 8. Do all this lovely math together. I think I get 4400. Isn't that the name of a TV show? And 170, which is 337.46 something or other foot-pounds. Woo! Oh my god, there's more airplane ones. They're never ending. These planes just don't stop. I guess I don't need that anymore, huh? Alright, we got someone flying. That's way too big. Let's just start that over. Alright, we have someone who we want to be flying due south, okay? And let's see here, 40 mile per hour wind, bearing of 30, so that's going to be right here, so that's a direction angle of 60, okay? So this is the wind, this is the result, or the ground speed, this is the plane or the air. What direction should this person fly in order to make sure that they fly south? So if we're being pushed kind of upwards, okay, at that angle, my guess is that we're going to end up somewhere over here. So that if I'm pointed this way, as that wind hits me, it will push me ever so slightly south. And this one's kind of a trickier one to visualize because these are going in opposite directions. So it's a little bit trickier to see, but I'm pretty sure this is what's going to happen with them. So we have plane. What do we know about the plane? Oh, Gosh, we know nothing about it. This is so much fun. Totally misread the question. Wind we got, that's 40 cosine 60, 40 sine 60. And the result, we know it. It's going directly south, and it's flying at 450 miles per hour, so that's 0, negative 450. If you really want to, it is officially 450 cosine 270 and 450 sine 270. Gets you the same exact thing. So let's see here. What can we find first? Doesn't matter. Let's find x. So it would be x plus 40 cosine 60 equals 0. So I'm just going to subtract the 40 cosine 60 to the other side, and I'll get that the x value is going to be negative 20. Do the same exact thing over here. Y plus 40 sine 60 equals negative 450. So I'll just do negative 450 minus 40 sine 60. I'm going to get the y value is officially, without a calculator, don't worry, you'd have a calculator. It would be that, which is negative 484.64. Let's see, what are we trying to do? What speed would we need to be flying here, and what direction? Okay, so speed, I'm just going to do 20 squared plus 484.64 squared in the calculator. I'm going to get this exact value here. So the plane itself needs to fly at approximately 485.0535 miles per hour in order for it to move directly south. For the bearing, I know I'm running out of room here, so I'm hoping that you can actually still see this. I'm going to do tan theta equals y over x, and I'm going to get theta as a reference angle, which was negative 87.63. I'm just going to make it positive. And then because we were pretty positive that we were actually going to be up here in quadrant 3, and I have to do a bearing from here, I'm going to do 270 minus that theta reference in order to figure out this bearing, because reference angles always connect to x-axis, so I need to get to an x-axis. So 90, 180, 270, and then subtract the theta reference angle. And when I do that, I'll get 182.36. So that's the direction the plane needs to point itself, going at 485 miles per hour for it to result going directly south. So it's a variation on one we've already done. That's kind of fun. I'm going to have those work songs stuck in my head all day. Aw, fun. Dory can swim 4 miles per hour in still water. She is swimming at the surface of the water northward. Okay, so Dory's chilling right there, going north at 4 miles per hour. The current in this situation is going 10 degrees north of east. Okay, fun. That's right here. 3 miles per hour. So this is the current. And we want to figure out which way is Dora actually going to be swimming in here. Dory, not Dora. What are we doing? Dora the Explorer here? My goodness. All right, so Dory, her vector is going to be 0, 4, because she's going straight north, so 0 in the x direction, and we just 4 in the y. The current is going to be 3 cosine 10, 3 sine 10. Add those together, it's going to give me the result. Okay, so I'll just use my calculator, and I got 2.9544 and 4.5209. I want to know how fast is Dory actually swimming, so I will do the magnitude of the result, a squared plus b squared square root 5.4 miles per hour. Okay, so she's actually going faster, and that's because they're kind of working together. And now for this bearing, right? So let's see here, positive, positive, so I know I'm going right here. So I'm going to find this reference angle, but I want the bearing, which is going to be up here. Okay, so I'll do tangent theta equals that 4.5 over the 2.9. I'll use the exact values in my calculator. I will not be rounding anything. And I'll get that theta is 56.84. And so then the bearing is just going to be 90 minus that reference angle. okay, which would be 33.61. Yay! Do, 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 do. Oh my god. We're so close, yet so far. Alright. Bringing back these from, like, I don't know, before the midterm maybe? Haley travels 10 miles, bearing of 108. Okay, so that's going to be right here, 10 miles, 108, that's 18 past 90. And then turns and travels 12 miles in a bearing of 198. Okay, so 198 is going to be somewhere here. And I don't quite know where it lines up. So I'm not sure if it lines up directly north-south or not. I'm not positive. I'm going to call that D there. This is going to be 18 by alternate interior. Let's see. I'm pretty sure this is 18 by, right? Because it's going to be 198. So that's 18 as well. And let's see here. We can actually use vectors to solve this rather than using law of cosines or law of sines. So I can write a vector for this side length up here. So that would be 10 cosine negative 18. Easiest way of writing that one. 10 sine negative 18. Now for here, I have two options. I can get the direction angle by going that way, or I could just go this way, which is going to be easier for me to think about right this second. I don't have a calculator in front of me, so I'm going to do negative 108, 90 plus 18, and then 12 sine negative 108. And I just add these together, and what that's going to give me is this vector over here that represents this, okay? So that's 5.8024, which I'd store, negative 14.5028, also store it. So this is what the vector D would be. And I want to just find its magnitude, a squared plus b squared square root, and I get 15.6205. So that's how long this side length is right here. And now what I need to do is just figure out what the bearing would be. So I'll do theta is tan inverse of that y value over the x value, again, using real values, don't round here. And I would get negative 68 point something. I'm going to make it positive 68.19. Let's see, positive x, negative y. That means that we are actually in the fourth quadrant. So here is theta. So the bearing is 90 plus that theta reference angle, which is going to be 158.19, which is the bearing from the start to the end, because that's the way these vectors are pointing. Okay? Woo! That's kind of a fun one. So we don't need to do law of sines and cosines if we didn't want to. We could use vectors. Really, it doesn't matter. Honestly, law of sines and cosines is probably easier, but okay. Oh gosh, just put that. Let's do another one of these. $17. Travels 2 miles, bearing of 310. Okay, so let's see, a bearing of 310. I started that in a bad place. So let's see, this would be 90, 180, 270, so 310 is going to be somewhere right here, so that's going to be 2 miles. We went 310, so that's 40 past the 270. And then we're going to turn, walk for 3 miles at a bearing of 40. Okay, so that would be 40. That means this part right there is 50. This is going to be 3. Okay, so alternate interior, that's 40. That makes this 90 degrees. So I have a big old right triangle here. Very poorly drawn, but that's what we have. And we want to figure out, let's see, if she had gone directly from start to end, how far would she have gone and what bearing should she have needed to travel? So we could just use right triangle trig at this point to figure out some of this, but I'm going to use vectors because that's what we're doing. So we started here going this way, so that's going to be 2 cosine, and I need a direction angle, so this is going to be 140, 2 sine 140. Then we're going this way, okay, so that's going to be 3 cosine 50, 3 sine 50. Again, I'm using the direction angle. If I add these together, I'm going to get 0.3963 and 3.5837. So that is going to be what this vector would be. And if I did a squared plus b squared, I will get that is going to be, I don't know, I didn't write it down, I only wrote down the exact answer. It's going to be whatever this is as a decimal, I have no idea. We need to find the bearing. Okay, so these are both positive, so we're in quadrant 1. So once I find the reference angle by doing theta equals tan inverse of 3.5, using the exact value, don't round, over 0.396, I will get that it is going to be 83.69. So I will do 90 minus theta, because that would be what the bearing would be. So that is like 6.3 degrees. Okay, so we could have figured that out as well. This right here would have been 6.3, I believe, and this one right here would have been the 83.69 if we were not using vectors, but here's it with vectors. Fun. Oh my gosh, my question. So exciting. Dr. G travels 10 miles at a bearing of 100 degrees. Okay, so I'm starting way up here, going 100 degrees. That's 10 right there, and I'm going for 10 full miles. Let's see. Travels another 8 miles, bearing of 200. Okay, so that's going to be right here. That's 20 past, and this is going to be 8. Don't quite know where I'm ending down here, so I'm just going to kind of stop somewhere. How far away am I? So I need to figure out that value, and I need to figure out what the actual bearing is from beginning. If I then head directly back, so I'm actually looking from here upwards. That's a little backwards than what we might normally do. So I'm going to do 10 cosine. I'm going to use negative 10 for that direction angle because it's the easier one to use. 10 sine negative 10. Then we have 8. Let's see, this is going to be 270 minus 20. So that's 250. So cosine 250. 8 sine 250. Add these together, I'm going to get 7.1119, negative 9.254. I'm storing these values. A squared plus b squared square root to find this actual distance. Okay, so that's how far away I am from wherever I started. And if I were to figure this out, here, this is an important thing. So we found the vector pointing this way, and the question is actually asking us to go in the exact opposite direction as this. So let's just find the reference angle first, and then we'll talk about what that means. So tan inverse of the y value, negative 9 point whatever over 7 point whatever, again using actual values, I would get 52.45 degrees. So we just found this one, okay, with that theta right there, but what we want is the opposite of this, because we're saying I've ended up here, I want to go back to where I'm starting, so I need the arrow to be pointing that way. So I need it to be going directly that way, and so that would have the same reference angle right there by those vertical angles that we got going on there. So a bearing in that quadrant would be 270 plus the reference angle of 52. So 270 plus 52, and I'm pretty sure that's 322.4569. Okay? Now, the answer key found the purple bearing and then just added 180 to it to rotate it around. Whichever way you want to do it. Woo! We finished. Oh my goodness. I'm exhausted. Yay!